Hello, welcome to High Performance Computing on AWS. My name is Mark Duffield, and I am a Principal Solutions Architect focusing on high performance computing and semiconductor design workflows. I have been in HPC for about 20 years, working on a variety of tightly coupled and loosely coupled workloads. I'm currently working with customers on many verticals and segments, from weather forecasting to EDA to structural analysis, to help them move their HPC workloads over to AWS. As this webinar is only about 35 minutes, there's not going to be a lot of detail to the presentation. But if you have questions or if you have any concerns about the content, please reach out to myself or another AWS HPC resource. So at AWS, we start with the customer's application and we work backwards. So rather than taking an AWS solution and making your application fit, we start with your application and we design a solution around the specifications required. At the end of this presentation, hopefully you can start architecting a solution for your workload on AWS. So today, I will talk briefly about our infrastructure and speak to our regions and our global footprint. And then I will discuss why you should be moving your workloads to HPC workloads and EDA workloads to AWS. And from there, I will dive into the components to enable HPC workloads. And then I will talk about the automation and batch processing that you can leverage, as well as how to launch HPC jobs. And I will also provide some customer use cases, as well as discuss a little bit on security and cost optimizations for HPC workloads. So with that in mind, let's take a quick look at our global infrastructure. At AWS, we have regions, availability zones, and data centers. These are our regions. Currently, we have 18 regions, and within each of those regions, we have 2 or more availability zones. And then within those availability zones, we have 1 or more data centers. In addition to those regions, availability zones, and data centers, we also have over 100 global points of presence. These points of presence enable services like S3 transfer, Route 53, and CloudFront. Connecting our regions is a redundant, private capacity 100 gigabit network. So diving a bit deeper into our infrastructure, this shows the number of availability zones within each region, with most regions having 3 availability zones and 1 region that actually has 6. Also noted on this slide are 4 announced regions in Paris, China, Sweden, and Hong Kong. And we're not even close to being done expanding. We will continue to add infrastructure. Why should HPC workloads run on AWS? Well, at Amazon, we're actually running a wide range of HPC workloads on AWS every day, from logistics and supply chain optimization to machine learning using Alexa. We are also designing our own data centers and our own proprietary network, as well as doing our own server design. And we also have our own semiconductor team that designs chips for the next generation of infrastructure at AWS. So why should you run your workloads on AWS? Well, at AWS, you have access to virtually unlimited infrastructure. This allows you to scale on demand very quickly, and you will only pay for what you use. For an on-prem installation, you are limited to the fixed size of your cluster. If you need to go from 100 instances to thousands of instances in minutes, AWS enables this elasticity. If you are 2 weeks late on a tape out, you can scale your cluster in minutes to meet your deadline. Also, the agility of AWS allows you to fast fail, iterate quickly, and reduce time to results. Before, it would take 2 to 3 months to procure a server, set up the power, the networking, and everything you need to get that server to come up, just to find out that you ordered the wrong hardware. At AWS, that process takes minutes, so you can quickly determine if you are using the right resources for your HPC workloads. And because you are only paying for what you use, you can ensure you are optimizing cost savings. And with our global footprint, you can increase collaboration with access to clusters from around the world. This results to faster time to results and a better return on investment. So in comparison, looking at running HPC workloads on premises versus AWS. Now, historically, HPC systems have been one monolithic system with one queue and long wait times. If R&D wanted to try something completely out of scope, they may have to wait for a long time before they ever can see results. If an intern wanted to test a theory, their submitted jobs may not even run before their internship is over, which is a true story. On AWS, you can have multiple clusters. Everybody gets a cluster. So now, production has their own cluster. R&D, they have their own cluster. Dev test, they have their own cluster. If accounting needs to run a Monte Carlo simulation to determine if the next acquisition is viable, well, now they have their own cluster. If logistics needs to run a forecast to determine best and safest routes for drivers, they get their own cluster. And for semiconductor design, you can now separate different EDA workloads onto different clusters. At AWS, agility and scale enable HPC workloads to innovate in ways never thought before possible. So now that I've covered the why, let's talk about the components that you will need. At the center of running your HPC workloads on AWS is the Elastic Compute Cloud, EC2. Our EC2 instances are optimized for different workloads to include compute, storage, memory, and accelerated optimizations. Networking is a vital component in this space, and we have a low latency, reduced jitter network that has high bandwidth that enables HPC workloads. For storage, we have several options that allow customers to choose from object storage using Amazon S3, block storage with EBS, or file system using EFS. To automate the launch and management of clusters, you can use AWS Batch, CFN Cluster, or AWS Nice Engine Frame. And finally, to visualize your results, you can leverage AppStream or AWS Nice DCV. So diving deeper a bit on EC2 instances, choosing the right instance type is important for optimizing price performance of your workloads. We have the widest range of compute instances and have recently announced some very exciting instance types. For compute optimized instances, we announced at reInvent the C5 instance that has 36 cores and 72 vCPUs, and I'll dive a bit deeper into the C5 instance on the next slides. For high I/O, we have the i3 instance that has 8 NVMe volumes and has a local throughput of 16 gigabytes a second and over 3 million IOPS. For accelerated workloads, we have our P2, P3, and F1 instances. The P3 instance uses the NVIDIA V100 Volta GPU, with the largest instance having 8 GPUs, and each GPU has 5,120 CUDA cores and 640 tensor cores. And the F1 instance is our FPGA instance, using the Xilinx UltraScale FPGA. At reInvent, we also announced Bare Metal, which allows customers direct access to physical server resources. So at AWS, we are continually iterating on behalf of the customer. And as an example of this was our original architecture of our EC2 instances, with the network, storage, management, security, and monitoring all on the server. So our goals were to increase security, increase performance, but also provide a familiar environment that customers would recognize. As part of the release of C3, C4, and C5 instances, we moved the network and storage components along with the management, security, and monitoring to specialized hardware. And what remains on the server is a thin hypervisor. We call this the Nitro system. The Nitro system improves security and frees up resources, so the customer can use nearly 100% of the resources on the server. Annapurna Labs, an Amazon company, designed a custom ASIC that was made for the Nitro system. So now looking forward at the compute optimized instance C5 and how it compares with the previous generation C4. So the C5 has 72 vCPUs, which is twice as much as the C4. And a vCPU is an Intel hyperthread, so the C5 has 36 cores. It has the Skylake processor that supports AVX 512. It has 12 gigabits of EBS throughput, which is 3x that of the C4. And it has over twice the amount of memory that the C4 has. As mentioned in the previous slide, the C5 has the Nitro system and 25 gigabits network connectivity. The C5 instance will enable many HPC applications to run and scale on AWS. For accelerated computing, we have our P2, P3, and F1 instances. As mentioned, the P3 instance has the NVIDIA V100 Volta GPU, with the largest P3 instance having 8 GPUs. These are supported by a wide variety of ISVs and open source frameworks, reducing the effort needed to accelerate HPC workloads. The F1 instance is an FPGA accelerated instance that provides easy access to configurable hardware. The F1 instance has the Xilinx UltraScale FPGA. It allows customers to use custom bit widths, a mix of instruction sets, or no instruction set at all. And there are many ISVs that are producing images for the FPGA. So rather than learning how to program an FPGA, HPC customers can now use the marketplace image to accelerate their workloads. Another example is machine learning. Foundries can use these instances to determine if manufacturing is meeting their expected yield. So the next component in this, and moving your workloads to AWS, is networking. So as part of innovating on behalf of our customers and operating at the scale that we do, we've developed our own proprietary network. The initial release of enhanced networking was 10 gigabits. This networking delivered low latency, reduced jitter, and high throughput. With the announcement of the Elastic Network Adapter, traffic between instances is now up to 25 gigabits for multi-flow. This is bisection bandwidth within a placement group, and there is no network oversubscription. AWS customers can now benefit from a predictable, low latency, high bandwidth network to run their HPC workloads. Additionally, traffic to and from S3 can now take advantage of up to 25 gigabits of bandwidth. So we've talked about compute instances and we've talked about networking. And so starting to bring this all together, let's talk a little bit about storage. So at AWS, storage is a platform. You can store your data using file, block, and object storage. For file storage, there's Amazon EFS, Elastic File System, that allows users to launch a petabyte scale file system in minutes. For block storage on the EC2 instances, we have either Amazon EBS, Elastic Block Store, or Amazon EC2 Instance Store. These block devices are used for the root volumes on the instances, but can also be used to build your own file systems. You can also store your data in object storage using Amazon S3, S3 Infrequent Access, or Amazon Glacier. And there are several ways of moving your data into AWS as well. For HPC customers, having at least a VPN connection is usually necessary, but using a direct connect or multiple direct connects facilitates large data movement between AWS and your on-prem systems. If you have hundreds of terabytes or even petabytes of data to move, you can leverage AWS Snowball solutions that can move up to 100 petabytes of data. So at Amazon, S3 object storage is a foundational service. So for the HPC space, this is where nearly all of your data will start and where it will reside. Once your data is in Amazon S3, you can determine how your applications will use that data. If your application supports object access, you can access your data directly from the instances of 25 gigabits a second. If your application requires a POSIX file system, as most HPC applications still do, you can use an EFS file system or build your own file system using AWS instance types that are designed for high I/O. And looking more at POSIX-like file systems, here are some file systems HPC workloads can use on AWS. Elastic File System, EFS, is our file storage product that is a petabyte scale file system. You use an NFS 4.1 interface to mount EFS, and it is a fully managed service and can be launched in minutes. It is designed to be highly available and highly durable. EFS stores data and metadata across multiple availability zones in a region to prevent data loss from a single component. EFS has many features that HPC workloads can take advantage of, such as file sync and the ability to mount your EFS file systems on-prem. Use cases for EFS would be M&E processing workflows, software development tools, and home directories. If you would like to compare your on-prem environment with AWS, building your own NFS filer can be used for POC workloads. Using our i3 instance, you can build your own NFS server for ephemeral data and tear down the environment when your POC is complete. HPC clusters have been using parallel file systems for decades, and the need for POSIX-like parallel file systems is still needed for certain HPC workloads. And you can still build your parallel file system or leverage solutions from one of our partners on AWS. And we have a lot of examples of this now. Now that we have covered all the components of HPC Solutions on AWS, how do we actually use it? How do we start to bring it together? There are many schedulers and batch management systems in the HPC space. On AWS, you can bring those systems when you're moving your workloads, or you can design your system leveraging the breadth of services that AWS has to offer. For example, you can use SQS and CloudWatch to monitor and signal auto-scaling to add resources on demand or using the spot market. Additionally, as a result of being able to launch multiple clusters and segmenting workloads, you should really consider if you actually need a scheduler. AWS Batch dynamically provisions compute resources based on the volume and requirements of the submitted jobs. It will plan, schedule, and execute your batch jobs across resources. There is no batch computing software to install, allowing you to focus on your applications and your results. And there are many tools for automating the process of launching an HPC cluster or workload on AWS. You can use CFN Cluster to launch a supercomputer in minutes, which includes several options for schedulers. CFN Cluster will dynamically auto-scale as your job requires, which optimizes cost savings without sacrificing performance. AWS Batch, mentioned in the previous slide, plans, schedule, and runs your batch jobs. For visualization, you can use AWS Nice DCV and Engine Frame. You can also build your own CloudFormation templates to automate this entire process. So you can do the running, the monitoring, the tracking of all of your HPC workloads, just building out your own CloudFormation templates. We also have a number of ISV offerings and system integrators that can help you run your workloads on AWS. So far, we've covered the necessary components as well as the automation tools for HPC workloads. So let's really try to put this all together. And this architecture represents a fairly simplistic view of what HPC might look like on AWS. But at the center here, you have an auto-scaling group that will dynamically scale as needed. So I'll walk you through the process of how this would work. So first, a user will submit a job. Now, if the cluster does not have the resources needed to be able to run that job, it will add the necessary resources to be able to run the job. So once the job is run, or I should say, as the job is running, you can use Elastic File System, a local NFS filer, or a parallel file system to actually write that data out. But when the job completes, you move that critical data up to S3, and you can either take those file systems out or you can leave them for another job. Now, if there are no more jobs left in the queue, the auto-scaling group will terminate the instances. So this is a great example of optimizing costs with HPC workloads. So the auto-scaling group can leverage any pricing model to include the spot market, where you can save as much as 90% off of the on-demand price. If you need to use visualization software to analyze your results, you can use one of our GPU optimized instances and AWS Nice DCV. So on the left, you can think about that modeling cluster piece there as the cluster that we just went over in the previous slide. And from there, you can use several GPU instance types to enable visualization, but still optimizing for cost. So now that we've covered the why and the how to run workloads on AWS, let's dive into a few of the use cases. So from Monte Carlo simulations to genomic processing to structural analysis, AWS customers are running a wide range of HPC workloads. So diving deeper into to some of these workload types, this slide is a great reference for these different workloads. Customers are running tightly coupled, loosely coupled applications, as well as accelerating their workloads using P3 and F1 instances. And then from there, customers are analyzing the results using visualization and deep learning. So AWS on HPC is working with nearly all HPC workload types. And for specific verticals, we are helping many HPC and EDA customers. You can probably find your vertical or workload here. So a few examples here are engineering simulations or semiconductor design, of course, weather forecasting and modeling, and genomic processing and computational fluid dynamics, seeing great success in all of these spaces right now. So now diving into a few specific customer use cases. Aon Benfield Securities uses a proprietary Monte Carlo simulation running millions of times. In the process of moving its infrastructure over to AWS, ABSI was able to deprecate its co-located data center. And for their architecture, they built a process to automatically launch GPU instances with EVS volumes, which provides the front-end system to their processing solution. The result is that they were able to reduce a 10-day process down to 10 minutes and created a process that can be as much as 500 times more efficient in terms of performance per dollar. Now, Celgene. So Celgene highlights some of the typical constraints that you would find in an on-prem HPC installation. Because they were using a fixed configuration, they were seeing long queue times and slow time to results. They also have security and compliance requirements because they collaborate with external entities. Now on AWS, they are really taking advantage of the ability to iterate quickly. For their architecture, they are using Amazon VPC, IAM, and Direct Connect to collaborate securely. Their HPC workloads use hundreds of EC2 instances and store hundreds of terabytes of data on Amazon S3 and Glacier. The result is that their HPC jobs have been reduced to hours instead of weeks. And now Celgene researchers are asking questions that weren't possible before. So now working with Rescale, who is an AWS partner, Boom ran simulations using 200 million cell models over 512 cores. And in the process, they were able to eliminate server capital costs and in-house IT and software costs. Their architecture includes elastic HPC capacity and pay-as-you-go AWS clusters, which enable business agility and scale. The result is that Boom has increased simulation throughput with 100 jobs in parallel at 6x the speed up, and was able to see a 600x speed up for their entire workflow. This use case truly highlights the accessibility of the accelerated instance types. Using our F1 instances and Edico's Dragon Genome Pipeline, the Children's Hospital of Philadelphia set a world record by processing 1,000 genomes in 2 hours and 25 minutes. Now, this customer is amazing. So Clemson University, working with Omnibon, who is an AWS partner, used software infrastructure based on Cloudy Cluster to provision HPC clusters on our Spot fleet. Specifically, this research was focused on topic modeling, which is an important component of machine learning associated with natural language processing. The result is that Clemson University was able to launch an HPC cluster with 1.1 million vCPUs on our Spot fleet. And this was done in a single AWS region. This ability to scale is enabling breakthrough scientific discovery, and papers describing the full study are being submitted for peer review publication. So now I'm going to switch gears a little bit. So now we've covered a lot about HPC, a lot about HPC on AWS, all the components, bringing that together, the tools, covered a few of the use cases as well. But I'm going to switch a little bit to security because I know in this space that customers are very concerned with security. So at AWS, we have the shared responsibility model. AWS is going to be responsible for the security of the cloud, and the customer is responsible for the security in the cloud. So we will secure everything up to the hypervisor, and then from there, we're going to ask the customer to secure their operating system, configure their security groups, network ACLs, IAM, and any other settings that are going to be relevant to their environment. We're definitely going to help you with this. We can definitely give you all kinds of pointers. We can bring solutions architects on site, give you all the help you need to secure your environment the way you want it. But you are going to be responsible to determine what and how you're going to specifically secure. And these are some of the compliances that we have at AWS that can enable the most security conscious customers to run workloads. And we are continually working with customers to determine if there are additional compliances that we can obtain. And at AWS, it is always your data. Customers choose where to place their data. So our regions are geographically isolated, and we don't replicate the data between the region unless you specifically tell us to do so. And the customer is always going to own their data, their ability to encrypt it, the ability to move it and delete it. You can, and speaking more about encryption, you can encrypt your data from end to end using a VPN or direct connect. You transfer your data over an encrypted pipe where it can be encrypted at rest on the EC2 instance. And from there, transfer to other services can also be encrypted. And this can all be enabled using our key management system or cloud HSM. And this can be done using your keys or a fully managed KMS. So briefly talking about media destruction. Media storage devices used to store customer data are classified by AWS as critical and treated accordingly as high impact throughout their life cycles. AWS has exacting standards on how to install, service, and eventually destroy these devices when they are no longer useful. When a storage device has reached the end of its useful life, AWS decommissions media using techniques detailed in the NIST 888. Media that stored customer data is not removed from AWS control until it has been securely decommissioned. And so now we've covered a lot of topics here, and there's a lot of content here. And again, please don't hesitate to reach out to us for more information, but I will touch briefly on cost optimization and some of our options there. AWS offers 3 core purchasing options: on-demand, reserved, and spot. Each of these options launches the same underlying EC2 instances. A recent announcement was that compute capacity is now paid for by the second rather than by the hour. This allows customers to truly optimize for cost. For on-demand pricing, you want to target spiky workloads that are generally not predictable. You are only paying for what you use, but running all of your HPC workloads using on-demand may not result in cost optimization. Now, if you have predictable workloads that you know that you're going to be running for several years, you can use our reserved instances. This option is a significant discount off the on-demand price. And we also have spot instances. Now, spot instances can save as much as 90% off the on-demand price. The spot price is set by Amazon EC2 and adjusted gradually based on supply and demand. To compare the spot price with the on-demand price, visit the Spot Instance Advisor. To minimize cost, HPC customers should consider using a blend of EC2 instance purchasing options. So in this example, a company is doing weather forecasts and modeling. Now they should be using reserved instances for the round-the-clock forecasting, but then during work hours, the weather scientists, they should be using the spot market and running climate model jobs leveraging the spot market. But when a major weather event occurs, they should use on-demand instances to increase the resolution and the frequency of the forecasts. And because I think I really know my audience well, I know that they're going to be interested in our data centers. And so we don't offer tours of our data centers. In fact, it's very difficult to get anywhere near our data centers. You have to have a very specific reason to get to one of our data centers. But we do offer the ability to take a virtual tour of our data center. And this shows a virtualization of one of our data centers. So the pictures themselves are real, but if you look closely there, that's a virtualized data center. And hopefully it gives some insight into how much effort and time goes into designing our data centers. So now I know that I've gone through quite a bit of material here, but hopefully there's enough material here that you can actually start thinking about how you would architect your solution for your HPC and EDA workloads on AWS. And I'm really excited about helping customers with their HPC workloads. I've been doing this for 20 years. It's a passion of mine, and I would love to hear from you. So please don't hesitate to reach out to myself or another AWS HPC resource. And thank you.